Okay, we have a situation that's the toughest one yet. Bernie the block has been pushed around, pulled around, so it's time for him to go sledding. If we put our block on an inclined plane like this, something where it's inclined, they often tell us the slope of the incline. I'll stick with 30 degrees because we can do it in our head. And I'll stick with some of the same parameters. If I have a coefficient of friction of 0.4, and if the block still has a mass of 10 kilograms, and if my angle is 30 degrees, now, usually my next step is to draw in my forces. I'll do that. Gravity always acts straight down. The normal force does not act straight up. The normal force is called normal because it is perpendicular, orthogonal, or normal to the surface, which means it's like perpendicular. So now we have gravity and normal that are not acting both in the y direction. And finally, we have friction. Friction always opposes sliding motion. So if we were dragging the block up the ramp, friction would be pointing down. But because the block would tend to slide down the ramp, friction acts up the ramp. Now it would be tempting to put an arrow pointing down because you have the sense that something is pulling this block down the ramp. But that is not a separate arrow. In fact, what's pulling the block down the ramp is the part of gravity that acts down the ramp. We'll get to that in a second. So don't go drawing any other arrows here. So it's just normal force, gravity, and friction. Okay? Now, what makes this problem challenging is if I think of y as being up and x as being side to side, my force of gravity is the only one that is purely in an x or y direction. My normal force would have x and y components. My friction force would have x and y components. And that's just kind of a pain in the butt. So what we're going to do is tilt our axis on its side. We're going to choose to call y off the ramp, and I'll choose to call x down the ramp. There's no reason why I can't change the orientation of my axis. So x is now parallel to the ramp and y is perpendicular to the ramp. And that means the normal force is all y, the friction is all x, and where the block slides is all x, so I'm going to get an x acceleration. The only one that becomes a challenge is the force of gravity. So let me expand this a little bit. The force of gravity is going to have some part going into the ramp and some part going down the ramp, and we see a similar triangle as some that we've seen so far. So if I make this bigger, if that's the force of gravity, and this is the force of gravity that's acting into the ramp, and this is the force of gravity that's acting down the ramp, I get a right triangle, and I get FGY and FGX. Now, because the angle here is 30 degrees, the angle here is 30 degrees. We have not congruent triangles, but similar triangles. This triangle and this triangle are similar. This angle is the same theta as this one. Ask your geometry teacher to prove that to you. So if that's 30 degrees, then this is the opposite side. So FGX, opposite of the angle, will be FG times the sine. Remember, the sine is the one dealing with opposite sides. And what is that? If Bernie is 10 kilograms, we have 100 times the sine of 30. This is 50 newtons in the x direction. And FGY, this component of gravity that's acting in our new y direction, will be the force of gravity times the cosine of the angle. So force of gravity is 10 times 9.8, or about 10, so I'm going to get about 100 there. Cosine of 30, we know that cosine of 30 degrees is 0.866, or about 0.87, so this gives me about 87 newtons. And just remember, if you're doing these calculations on your calculator, and if you're using degrees, make sure your calculator is set to degrees. On a TI-84, you do that by going to Mode and go down here. Make sure you're not on radians. Make sure you're on degrees. This might be a pain for people who are later on in pre-calc, because sometimes in pre-calc you use radians, but for these we're going to use degrees. Okay, so we have our two components of gravity. Now, we did our first step, draw in our force diagram. We did our second step, work out any angles, so we now know what those are, the angled force. Now we can set up our Newton's second law in X and in Y. The sum of all forces in X equal ma. The sum of all forces, what have I done? The sum of all forces in Y equal ma. Okay, so looking at my diagram, what forces act in a positive X direction? Now, there's probably some physics books that would say going up the ramp should be positive and going down the ramp should be negative. But I say the direction it's going to accelerate is where I want to call positive. That way I get a positive acceleration. So I'm going to say the force causing an acceleration in the X direction is Fgx. So I have Fgx going down the ramp minus the force of friction. And that equals m times a. Now I'll pause and make a comment here. There are times when we don't know the mass, or we don't know an angle, or we don't know some other variables, and it would be a good idea to leave some of these things as variables. For instance, Fgx, I might choose to write mg sine theta. And force of friction, I might choose to write mu times the normal force, and so on, and leave these things as variables, because sometimes variables will cancel out, and that might actually save some work for you in the end. For right now, let's put in the numbers that we know. First, let's come over here in the Y. Looking at our diagram in the Y direction, which we're now calling off the ramp, we have normal force acting up, and we have not all of gravity acting down, but just Fgy acting down. And now I can say that the normal force is equal to Fgy, the force of gravity in the Y direction. Okay, I can start to write in some numbers. I know, for instance, that Fgy is 87. So that means for this problem, the normal force is also 87 newtons. I also know that m times g is 100 and the sine of that and so on. So Fgx is 50. So 50 minus 0.4 of 87 equals 10 times acceleration. Notice how I couldn't just solve this in the x direction. I needed the y to show me what my normal force was. The normal force in this case was not simply equal to gravity. It was equal to the y component of gravity. Okay, now that I know this, 40% of 87, 34.8. Subtracting 50 minus 34.8, I get 15.2, right? 15.2 equals 10a. And I see an acceleration that is quite a bit slower than the ones we've seen, 1.52 meters per second squared. I'd probably call it 1.5 for sig figs. Now, that's a pretty slow acceleration. And actually, it suggests that if this ramp were angled a little lower, if this was at 25 degrees maybe, it might actually be a point where the block wouldn't slide. What would cause the block not to slide? If the force of friction was greater than the force of gravity in the x direction. In other words, Fgx was 50, force of friction was 34.8. If friction was large enough to equal 50, then the block would not slide. It would be an interesting problem to figure out at what angle would the block only then begin to slide. that's another problem for another day.